Okay, so picture this, right? You're at a summer barbecue, flipping burgers, enjoying the sunshine, and maybe even letting out a sigh of contentment.
Ah, the simple joys of life.
Right. But here's the thing. Behind that simple burger flip, there's a whole lot of chemistry going on.
You've got combustion, energy release, chemical bonds breaking and forming. It's a microscopic dance party happening right there on the grill.
It's amazing how much we rely on chemistry without even realizing it. And speaking of amazing chemistry, you, our awesome listeners, have sent in Unit 1 of your VCE chemistry textbook. And we're diving deep into the world of energy and fuels, specifically for SAC 1.
So buckle up, everyone.
Ready to explore the chemistry that powers our world?
Absolutely.
Let's start with the fuels we use every day, those energy sources that keep our lives running. We're talking petrol, natural gas, even coal, which, by the way, still plays a significant role here in Australia.
Yeah, you're right.
What's the common thread between all these different fuels?
Well, at their core, they all store energy. Chemical energy that's locked away in the bonds between atoms.
Ah, those bonds, those tiny connections that hold everything together.
Exactly. And breaking those bonds, well, that's what releases the energy we use.
So when we burn these fuels, like in a car engine or a gas stove, we're essentially breaking those bonds and releasing that stored energy. That's what we call an exothermic reaction, right?
Spot on. Combustion is a prime example of an exothermic reaction. Fuel reacts with oxygen, bonds break and reform, and boom, energy is released as heat and light. And it's that heat we harness to power our world, from our cars to our homes.
But it's not all sunshine and burgers, is it? There's a flip side of this energy release, and that's those notorious greenhouse gases.
Oh, yeah, we've got to talk about those. Carbon dioxide, CO2, methane, CH4.
Yeah.
They're a big deal when it comes to burning fuels.
Why are they such a big deal, especially when it comes to climate change?
Well, think of greenhouse gases like a blanket around the Earth. They trap heat in the atmosphere, leading to a gradual warming of the planet. And that warming, well, it has a ripple effect, causing rising sea levels, more extreme weather events, and all sorts of other challenges.
So understanding how much of these gases different fuels release is critical for tackling climate change, right?
Absolutely. It's all about making informed choices and finding ways to reduce our environmental impact.
Okay, so how do we actually measure these greenhouse gases and figure out the environmental footprint of different fuels? How do we quantify it?
One way is through something called stoichiometry. Might sound a bit intimidating, but it's basically using balanced chemical equations. Think of them as recipes for chemical reactions to calculate the exact amounts of reactants and products involved.
So like a precise recipe for a chemical reaction.
Yeah, pretty much.
I like that.
And by applying stoichiometry to combustion reactions, we can determine the volume or mass of those greenhouse gases produced.
Stoichiometry helps us compare fuels and their impact on the environment. That's super helpful, especially for SAC 1, right? Okay, let's shift gears for a bit and talk about biofuels.
All right, sounds good.
We hear a lot about ethanol from corn or biodiesel from oils. Are these truly the green alternative they're often touted to be?
That's a great question. It's more nuanced than a simple yes or no.
Okay, I like where this is going.
Biofuels, you see. They are made from renewable sources, like plants, which is a huge plus. But the processes involved, things like fermentation for ethanol and transesterification for biodiesel, they still have their own environmental impacts.
This is where it gets interesting for me. Are biofuels truly renewable? I mean, if we're using land to grow crops for fuel instead of food, is that really sustainable in the long run?
You've hit the nail on the head. That's a big part of the debate surrounding biofuels. Land use, food security versus fuel production, and the energy required to process them. These are all crucial factors to consider.
I've even heard about researchers exploring algae as a potential biofuel source.
Oh yeah, algae biofuels, they're a fascinating area of research, holding a lot of promise.
But I imagine there are challenges too, right?
Oh, definitely. There are hurdles to overcome before they become mainstream. It's all about weighing the pros and cons and striving for the most sustainable path forward.
So we've got fuels, we've got biofuels, and a whole lot of chemistry to wrap our heads around. But the big question looming is, if we need energy, how do we make it sustainable? That's the million-dollar question, isn't it?
You got it. And that's where green chemistry takes center stage.
Green chemistry. Tell me more.
It's a field dedicated to designing chemical processes and products with sustainability as a core principle.
So instead of cleaning up pollution after it's created, we're talking about preventing it in the first place.
Exactly. Proactive, innovative, and focused on minimizing waste, reducing energy use, and using safer ingredients.
I'm already sensing this is going to be a big part of SAC1, am I right?
You are. Green chemistry is a game changer, and understanding its principles is crucial for SAC1. It's about shifting our mindset and paving the way for a more sustainable future.
All right, let's dive into those principles.
Let's do it.
Green chemistry operates on 12 guiding principles, right? Can you give us a sneak peek into one that you find particularly interesting, one that really stands out?
Well, one that always fascinates me is atom economy.
Atom economy.
Yeah.
Tell me more.
It's all about maximizing the use of starting materials in a chemical reaction so you have less leftover waste.
So making sure every atom counts.
Exactly. It's like making sure every piece of a puzzle is used so you don't have any stray pieces left over. Reducing waste, increasing efficiency, key elements of green chemistry.
I can see how that aligns with the whole sustainability goal. So are we talking about designing reactions that use as much of the reactants as possible to create the desired product, making those reactions super efficient?
Precisely. And this principle, it has far-reaching applications across various industries, from pharmaceuticals to manufacturing. It's about making smarter choices from the molecular level up. Atom economy is really a game changer, isn't it? It forces us to rethink how we approach chemical processes. But, there's another principle that I find just as captivating. Catalysis.
Catalysts.
Yeah.
Those substances that speed up reactions without being consumed themselves, right? They're like the behind-the-scenes heroes of the chemistry world.
Haha, I like that analogy. They're essential in so many industrial processes, making reactions more efficient and sustainable. They work by providing an alternative pathway for the reaction to occur, lowering that energy barrier, the activation energy required.
Activation energy, that energy hurdle that molecules need to overcome to actually react. So catalysts are like the ultimate wingman, helping those molecules get over that hurdle and react more easily.
Exactly. And because catalysts aren't consumed in the reaction, they can be used repeatedly. Talk about sustainability.
It's like they're the ultimate multitaskers of the chemistry world. Now, speaking of reactions, we can't forget about rates of reaction, how fast or slow a reaction happens, right? Another big concept for SEC1.
Absolutely. It's crucial for optimizing chemical processes. And one of the most fundamental theories that explains reaction rates is, well, collision theory.
Collision theory.
What?
It rings a bell from high school, but could you give us a little refresher?
Sure thing. It's all about molecules colliding, but not just any collision. They need to collide with enough energy and in the right orientation. Think of it like a game of molecular billiards.
Okay, so it's not just about molecules bumping into each other. It's about them hitting with enough force and in the right position to actually react.
You got it. And just like in billiards, we can adjust the conditions to increase the chances of those successful collisions, thus speeding up the reaction.
I'm intrigued. What kind of factors can we tweak to influence those reaction rates?
Well, one common way is by increasing the temperature. It makes those molecules move faster, bumping into each other more frequently.
So more heat, more energy, more collisions, faster reaction. What about the concentration of the reactants? Does that come into play?
Definitely. Increasing the concentration also increases the rate of reaction. More molecules packed into the same space, higher chance of collisions.
Kind of like rush hour on the freeway? More cars? Higher chance of a fender bender?
Exactly. And just like reducing space on the freeway leads to more collisions, decreasing the volume of a reaction vessel for gases increases the pressure, which, you guessed it, also increases the rate of reaction.
So pressure is like a measure of how crowded those molecules are. It all comes back to those collisions.
Yeah.
What about surface area? Does that matter too?
Absolutely. Increasing the surface area of a solid reactant exposes more of its molecules to those all-important collisions.
So grinding a solid into a powder, for example, would make it react faster.
Precisely. More surface area, more opportunities for those molecules to interact and react. And of course, we can't forget our star players, the catalysts we discussed earlier. They're like those skilled pool players, expertly setting up the shots for those molecular collisions.
So we've covered quite a bit here. Fuels, green chemistry, reaction rates, catalysts. Are there any other key concepts we need to have on our radar for SAC on?
Yes, one more crucial topic: reversible reactions and equilibrium. It's all about balance and stability in chemical reactions.
Equilibrium. It makes me think of a seesaw perfectly balanced in the middle. Is that a good analogy?
That's a great analogy. Equilibrium is a dynamic state where the forward and reverse reactions are happening at the same rate. It's not that the reaction stops, it's more like a constant dance between reactants and products, but the overall concentrations remain stable.
So it's a dynamic balance, a state of constant change, but also a state of equilibrium.
You got it. And this balance, this equilibrium, can be influenced by factors like temperature, pressure, and concentration. By adjusting these conditions, we can actually shift the equilibrium in one direction or another.
Interesting. So we can tweak those conditions to favor either the formation of more products or the reformation of reactants.
Precisely. Understanding these principles is key to optimizing chemical processes, especially when we want to maximize the yield of a desired product. Think of something like the Haber process, which is used to produce ammonia, a crucial component in fertilizers.
The Haber process, now that you mention it, I remember learning about that in high school. It's a classic example of how manipulating those equilibrium conditions can really boost yields, right?
Absolutely. By adjusting the temperature, pressure, and the concentrations of the reactants, we can shift that equilibrium towards producing more ammonia. This process has been revolutionary for agriculture, allowing us to produce fertilizers on a large scale to feed a growing population.
It's incredible how these seemingly abstract chemical concepts have such tangible real-world impacts. We've covered a lot of ground in this deep dive, from fuels and sustainability to reaction rates and equilibrium, all with an eye on what's important for SEC1.
It's all connected, isn't it? And it highlights how chemistry is woven into the fabric of our lives and the future of our planet. Understanding these principles empowers us to make informed decisions about the products we use, the energy we consume, and ultimately the sustainability of our world.
Yeah, it's really amazing to see how these concepts tie back to sustainability. It's like chemistry holds the key to a greener future.
It really does, and green chemistry is leading the way.
I feel like this deep dive has been super insightful, especially with that SEC1 focus. I have a much clearer understanding now of the key concepts and how they relate to creating a more sustainable world. What's one thing you'd want our listeners to take away from all of this?
I think the most important thing is to remember that knowledge is power. The more we understand about chemistry, the better equipped we are to make those informed decisions about our planet's future.
So true. It's about being curious, engaged, and not being afraid to ask questions and really dig deep. It's not just about memorizing facts for SEC1. It's about understanding how those facts connect to the bigger picture.
Absolutely. Chemistry is always evolving. There's always something new to discover.
So where do we go from here? What's the next step for our listeners who are feeling inspired to delve deeper into the world of green chemistry?
Well, I'd encourage them to explore those 12 principles of green chemistry. Research how they're being applied in different industries, and think about how they can incorporate these concepts into their own studies and even their daily lives.
That's a fantastic call to action. We've only just scratched the surface, and there's a whole universe of knowledge out there waiting to be explored.
It's been a pleasure joining you on this deep dive into green chemistry. Remember, chemistry is everywhere, so keep your eyes peeled for those everyday wonders that spark your curiosity.
Thanks for tuning in to the Deep Dive. We hope you enjoyed the journey as much as we did. Until next time, keep exploring, keep learning, and keep asking those questions.